Hello everyone, this is Mohsen Saraj from the Ozen Engineering team. Uh, I wanted today talk about the dynamic mesh motion, use of dynamic mesh motion in Fluent, specifically about piezoelectric actuators. So, what is piezoelectric effect? Basically, when we have piezoelectric material, if we applied the electrical field, we see the deformation into the material, or other way around. If we apply displacement to the material due to the deformation of the material, it could produce voltage. We can use these these features of these materials into piezoelectric actuators, that in this way we can have control mechanical displacement on force, and it could be repeatable in a precise manner and controlled manner. Also, we have multi-layer of the materials. Mostly these are crystals that from ceramics materials that we can put it together and build the actuators or motors. Some other application for use of piezoelectric materials, for example, we can have piezoelectric pump. This is a schematic shown here. Consider that when we have the motion, like a cyclic motion of the piezoelectric material, it could act like a vibrator that we can use it to suck in the fluid from inlet and then send out the flow from outlet. So we in this way we can use it as a pump to send out the flow from inlet to the outlet. Another application of piezoelectric actuators could be, for example, atomizer, like a ultrasonic atomizer that used when we put a mesh that it is comprised of many holes, or that act as like a nozzles. Below that, as you can see, we have we can put it on the top of liquid, and then a disc around a disc of piezoelectric disc, we can use it, and we have this mesh inside that. Then when we have the motion, like for example the induced motion due to the piezoelectric excitation that we have, when the when this wall, we call it wall, when it's going up, okay, this holes, then it is like a nozzle that suck in air into the water. And when we go to the next phase of the motion, when we have a downward motion of the walls, then uh, water can be ejected to outside, like here that you can see. When it is in very high frequency, like a ultrasonic frequency in megahertz, or in hundreds of kilohertz, we can use it as for the producing mist above here, or use it some exact dosage for some pharmaceutical application, from exact dosage of the drugs that we can use it for inhalation by the patient. So if you consider, if we back to this example, that you can see that we have these nozzles, that it is like a vertical motion that induced from the piezoelectric material. And if water is at the bottom, air in on the top, in this the same example with the fluid domain, then we have these moving walls between these nozzles, that we can apply the prescribed motion that we obtained from the piezoelectric actuator that we have. And in this way We can use it either for the pump or actuate atomizer or whatever application that we have. So as you can see, the boundary of the mesh is moving, so that sometimes we call it deforming mesh or moving wall for the mesh. uh, we in Fluent we have features that we call it dynamic mesh, that when is activated we can define motion for the boundaries of the mesh or for the specific zone inside the domain. And then if besides the dynamic mesh features, if we use it for uh, along with the multi-phase model, then we can go for the simulation of some application of the piezoelectric actuators, like for pump, atomizer, or other application that we have. A quick review of the main steps in Fluent. When we want to use dynamic mesh motion, we need an initial mesh. Be sure that here that we are working with the transient solver, and activate the dynamic mesh. We need some setup for the dynamic mesh motion, like a method that we want to use, is some options that we have that we can smooth out the mesh motion and keep the quality of the cells of the cell mesh cells during the motion, because we don't want to excessive distortion of the mesh shape or mesh size for after the motion that we have. And for sure we need a way to define this prescribed motion, that it could be either from profile, that one of the variable for sure is time, and another one is x, it is if it is horizontal motion, y if it is vertical motion, or together if it is planar motion, and if it is three-dimensional, then for sure we have x, y, z, and t components into the profile. We can use UDF also if we have the data points, and we can use it. uh, and for sure we need to preview the mesh motion. This is an example of the up and down motion of the moving wall of the mesh that we expected to see. It is like a cyclic motion, it is like a sinusoidal wave that we can produce due to the displacement or deformation of the piezoelectric material applied to these walls that we can see. So at the beginning it goes up and then going down, and then again going up, going down, and after, and then back to the original position. So it is like a two cycle of a sinusoidal wave. The good things about piezoelectric actuators that we have we can produce really a controlled motion with a specified amplitude and a specified frequency. So a quick review of what steps you need to do in Fluent. We need transient simulation. We need to activate the dynamic mesh feature in Fluent, is not activated by default, and these are the details that we need to work on that in to set up the dynamic mesh motion. We need to know what method we want to use, what options we want to use, if we need more setups for each of the method, smoothing, layering, remeshing. Here we need to define the moving zones, where in the mesh, in what zone, in what region we want to apply the dynamic mesh motion. And then we can use display and preview to mesh before starting the simulation, to be sure that the motion is in a way that we like it, and we don't see lots of distortion or unwanted distortion for the mesh element. We have some videos about that, about the setting up the dynamic mesh motion in Fluent. Please visit Ozen Engineering YouTube channel and look for these videos. that I just walk you through step by step how to set up a domain for appropriate for a mesh motion, and then the setup for the step-by-step setup in Fluent to assign the mesh motion and then preview the mesh motion. So now we can I can here I will quickly show you the geometry and where we apply the wall motion for the mesh, and then have to set up a model for a piezoelectric actuator. This is the geometry. These are the 10 holes, and at the bottom we have water, above is air. These are the holes, and I just partitioned for the each side for the water and air for meshing. So we use named selection, outlets on top, and we have to choose the where we have moving walls. Upper, you can see here, lower, holes, these are moving walls, and the walls that we have moving or sliding mesh. So this side, up and lower, and in the center. For meshing, workbench meshing is used. I use multi-zone, and the mesh it is for CFD Fluent meshing. You can see the mesh which is refined above the holes that we have. I use hexagonal mesh, and the metrics that it is based on orthogonality. You can see here the minimum it is 0.82, which is very good. Mesh statistics, it is about 500,000 nodes and about 250,000 elements or cells. Okay, Fluent model. We have transient simulation, and this is the mesh. Okay, as you see the nozzles up, we will assign air material, at the bottom water. About the model, I use VOF or volume of fluid method here. Two phases that we have. One phase it is primary is air, another phase is water liquid, and the phase interaction I just consider constant surface tension between air and water. For materials, I have air and water liquid. We start with air, constant density for the air. We can work on other models for the available material modeling for available for air, like ideal gas, but we start with just constant density, and same for water liquid, constant properties. So for here, as you can see, I already activated dynamic mesh and using smoothing and remeshing, and here I have many zones that I already created in and name it name this like a name selection, create these name selections in Ansys Discovery, and then I use it here. As you can see, in general I have two 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 types of the uh, moving zone. One, it is rigid body, that when we have the moving walls, and the forming zone it means that they are adjacent to the moving walls, and it is in this way we can allow the mesh that is sliding along that these walls. The details about this setup, okay, is fully explained in the another videos that I already created. This is Ozen Engineering channel partner channel here that we have on YouTube. If you go to the videos, okay, these are the this video part 3, part 2, and part 1. These are the videos that I created, and you can see the details above about the setting of the dynamic mesh motion for this model. Back to Fluent. Uh, be sure that here for the method of solutions we use piezo for coupling of the velocity and pressure, and also presto for pressure. We initialize the model, initialize that, one more to be sure that it is initialized, and then we patch water because it's already initialized with air when the volume of fluid is 0. So I need to patch the water into the domain at the bottom below these nozzles. So I, instead of mixture, I go to the phase water volume fraction. I define this region by cell registered that includes this part of the domain at the below the nozzles, below the holes between air and top parts and bottom parts. Patch it. Before starting, we can check the volume of fluid to be sure this is for water, and you can see in this way I just consider half of each hole or nozzle filled with water and half is empty or it is air. That here we have it. We can check volume of fluid method. Okay, no warning, the setup is correct. For before running the calculation, we can check the case, just about the general recommendation for the improving the mesh quality, that we already know that the mesh quality is good because the orthogonality is well above 0.15. And this time step, it depends to the frequency of the prescribed motion that we have. uh, I already, in physics, you can see that here you can define the profile. I already defined a profile that being assigned already to to moving walls, And we have two parameters, time and y components, which is bel belong to this cyclic motion. This is this sinusoidal wave. So I hit the I just hit the calculation button, and the solution is starting. I use k omega method, just the default value. This is the first time step. You see the iteration within first time step. And now second time step. I define already some monitors for solution reports. For example, this is for the velocity at the hole, the nozzles, max velocity, and also max velocity at the holes. About 85 time steps down. When we check the monitors for the solution, you are seeing that the average velocity at the nozzles, okay, it is 100, but the maximum it is quite high, which is 800. So we didn't expect to see such a high velocity, and that's why we have to revisit the material modeling that we are using for water and for air, and also be sure about a mesh that maybe we need a better mesh resolution compared to the prescribed motion that we have for moving walls in terms of the amplitude of the prescribed motion and frequency. And these are the and this is for the you can see that the air sucking in to the domain. It means that these walls here, okay, between the walls between the holes is going up. And as the walls going up, it means that the air sucking into the bottom parts. And in the next time steps, when these moving walls going up, okay, sorry, going down, then you can see that we can have like a water jets that exit these nozzles, and we have a kind of uh, water droplets water droplets that enter this region above the holes. Okay, the solution is completed, and as you can see, for example, for average velocity, we see the sinusoidal variation. It is in line with the cyclic motion that we have for the walls. And for the average, this is average value, and then this is the max value of the velocity in the domain, and this is max value for the holes or the nozzles. You can see that the velocity, max velocity, and so we have to think about some improvement that we need to do here. Let's look at the contours that based on that I created some animations. I'm going to show you the animation for VOF contour, and here you can see that the two cycle of the motion, okay, it is up to 20 microsecond, and after that we see that the velocity decrease, and this is because there is no other wall motion or mesh motion into the domain. and you see that it is just going to get into the almost very low velocity. Let's look at the volume of fluid contours that I created animation on that. And okay, if we decrease the speed for the play, you can see that the wall is going up, and so sucking in the air. And now in going down the wall, and we see the ejection of the, or like water jets from this nozzle or from these holes. And you can see that the air entering into the lower part of the domain is not the same for these holes. It depends to the water conditions that we have. And here we can see how far the the droplets are going. So we are in the second cycle that still the wall is going up or down, and we see that again another ejection of the water, like a water jet going up, and these are like droplets of the or air packets that are spreading into the air. And this is all the use, so we can model this from the dynamic mesh motion. Now we pass the time for the dynamic mesh motion. So as you can see, there is no change here in the entering of the air into the water, or ejection of, or sending out the waters from the nozzles, and we just see the traveling of the droplets into the air. If we increase the speed for the playing, okay, I hope you learn how to set up the model with dynamic mesh motion for this due to this prescribed motion, that it can be from a piezoelectric actuator, and for this type of the application that it is for uh, forming the droplets and forming the mist above the here above the the nozzles, above the holes that we are having here, that can be used in variety of application, like a pharmaceutical application for specify the dosage of the drug by inhaling, and prescribe for inhaling for the patient. So this is the first part of the video. In the next part, I'm going to show you some possible improvement to the model, that how we can decrease these hikes in the max velocity and improving the model. Please watch the second video as well. Thank you very much.